All right, welcome back, guys. I know we never wanted to do these again, but times have changed, and unfortunately, with all that's going on with the virus and stuff, some of you are quarantined. Maybe some of you, this is just a chance to review, but we're going to do a video instruction. This is going to be over 7.4. I covered this in class on Monday of week 11. I believe the date is November 16th. And so what I'm going to be doing is I'm going to be making videos again. Since so many of you are quarantined, I think this will be the most effective way. I think it'll help you kind of see what we're doing in class and get a firsthand taste. I know it's hard to just read through the book and read through the guided notes and really get the concepts. So we'll be doing this. Now, a little change you'll notice just solely for this lesson is the camera isn't on me. It's actually on page 299 of your book. So I'm going to be using that as an illustration as part of the lesson. So I would ask you to pause the video right now, get out your book, and turn to page 299. Okay? Once you have done that, we'll begin the lesson. So again, this is 7.4. So where are we at? Well, 7.2 we talked about, or let's back up even further. 7.1, we introduced the concept of a normal curve. What is it? And then how do we find the area under it for certain standard deviations? And that was the empirical rule. Then we learned in 7.2, how do we find the area under for any given value under the normal curve? If I give you a value, you can find the area for me, and we use normal CDF. We also learned how to standardize data. In 7.3, we flipped the script. We said, not only do I want to know how to find the area given a data value, but I also want to be able to find a data value given a certain area. I want to find the data value that starts a certain area happening or ends it. And then finally, here we are in 7.4. And as you can see on the screen, we're going to use normal distribution techniques to work with binomial distributions. And this is because working with normal distributions can be easier. Quite simply, think back to chapter 6. Binomial distributions can be difficult. The 1 minus, the when do I use PDF versus CDF, it can get tricky. And so what we're going to do is we're going to learn how to use normal distribution techniques to approximate binomial distributions. Now, how and why can we do this? Well, I hope you're looking at page 299 in your book. And you can see I have it illustrated here. You can see at the top of the page in figure 737 that I'm pointing at right here with my smartboard pen, you can see a histogram. And that's a histogram of a binomial distribution. You can see in your own textbook, 0.25 is the probability of success, 0.75 is the probability of failure, and then they calculate the mean and the standard deviation for the binomial distribution using formulas n times p and the square root of n times p times q that we've seen before, that you can find on the second page of your formula sheet. You also see the n value is 3. Now, what you'll notice, the difference between the graphs as we go through, is that the only thing that changes is the n value. The probability of success and failure does not change. We simply change the number of trials. Consequently, because the number of trials is involved in calculating the mean and the standard deviation, you will see that the mean and standard deviation values change, but it's only because we're changing the number of trials. And what you'll see is as the number of trials increase, as you're looking at your textbook on page 299, the histogram becomes more normal. It becomes more normal. That curve, that red line that they're using to estimate a normal curve, becomes more and more accurate with your data. And so the question becomes, looking back at your computer screen, how and when do we know that we can use a normal distribution to approximate a binomial distribution? Obviously, we shouldn't do it in figure 737, and it looks pretty good in 740, but what's the cutoff point? Well, the first thing I want you writing down in your notes is the following. If n times p is greater than 5 and n times q is greater than 5, then we can assume the binomial distribution is normal. Through a lot of hard work and testing, statisticians discovered this makes the adequate cutoff point. If n times p and n times q are less than 5, the binomial distribution cannot be accurately described as a normal curve. But if they're greater than 5, it can be accurately described by the normal curve. And I want you to test this. Look back at page 299. You'll see in figure 737 and 738, if you do n times p and n times q for each of those, the values will not be greater than 5. But for figure 739 and 740, the values will be greater than 5. And that should make sense. The normal curve adequately approximates the binomial distributions in the latter two pictures. It clearly doesn't in the first, and it kind of does in figure 738, but again, it's not quite symmetrical. So again, n times p is greater than 5, n times q is greater than 5. It's the first concept you got to know for 7.4. Okay, Mr. Carter. So we're approximating binomial distributions with our normal distribution techniques. So the question becomes, okay, we can do that because n times p is greater than 5 and n times q is greater than 5. What is that going to look like? Well, the first thing we got to do is we got to refine the mean and the standard deviation. Why are we finding the mean and the standard deviation? Well, because if we're going to use our normal distribution techniques, whether it's inverse norm or norm CDF, we have to know the mean and the standard deviation. Now, to find the mean and the standard deviation, because the distribution is binomial, we're going to use the exact same formulas we used in Chapter 6 to calculate the mean and the standard deviation for binomial distributions. The formulas don't change. To find our mean, we do n times p. To find our standard deviation, we do the square root of n times p times q. Again, if you would look back at your Chapter 6 notes for binomial distributions, these are the formulas for mean and standard deviation. So without further ado, let's do an example. Again, big picture here, we are taking a binomial distribution and we are applying our normal distribution techniques to it. So what are we going to do? Well, first things first, we just have a problem. The owner of a new apartment building must install 25 water heaters. From past experience in other buildings, she knows Quick Hot is a good brand. She also knows that the probability a Quick Hot water heater lasting 10 years is 0.25 or 25%. What is the probability that at least 8 of the water heaters last more than 10 years? Well, first things first, is this a binomial distribution? Answer, absolutely. And this isn't something I need you to be able to write down, but you do need to be able to articulate it. If I ask you if this is binomial, you need to be able to tell me why. And what I'm looking for there is two things. One, is there a success and a failure? Answer, yes. Either the water heater lasts 10 years, success, or it doesn't. It lasts less than 10 years, failure. Okay, two, are we selecting a certain amount out of our total number of trials? Answer, yes. We want to see if at least 8 of the water heaters out of the 25 last more than 10 years. That makes it binomial. So given the fact that it's binomial, let's identify our NP, Q, and R values. Go ahead and pause the video. See if you can identify NP, Q, and R. All right, check your work with mine. Well, my total number of trials would be the total amount of water heaters, which is 25. I'm choosing at least 8 of them. Okay, I want at least 8 out of the 25. That's the probability I'm looking for. P, the probability of success, 0.25. There is a 25% chance that a water heater will last longer than 10 years. Consequently, your probability of failure is 0.75. Okay, we've established it's binomial. We've pulled the data. Now, can we assume it's normal? Again, I want you to pause the video right now. See if you can go back and look through your notes that we've taken so far for 7.4 and establish whether this is normal or not. Okay, you've given it a shot. Well, I hope you came up with the fact that it indeed is normal. But what's the proof? Well, remember, in order to assume a binomial distribution is normal, we have to have n times p be greater than 5 and n times q be greater than 5. So I do n times p, 25 times 0.25, and I get 6.25, which is larger than 5. 25 times 0.75, Again, if I go ahead and calculate that, I will find that that is 18.75. Again, indeed bigger than 5. What this allows me to do is proceed as if the binomial distribution is a normal distribution. So, proceeding forward, I'm going to identify the mean and the standard deviation. These are essential whether I use inverse norm or norm CDF. Any normal distribution, I need to know the mean and standard deviation. Well, they didn't tell it to me, but because it's binomial, I know how to calculate it. The mean of any binomial distribution is n times p. Well, we already found n times p, and it was 6.25. The standard deviation is the square root of n times p times q. So I do the square root of 25 times 0.25 times 0.75. When I do this, I get a standard deviation of 2.17. So now we come to actually solving the problem. We've set the scene, so to speak. We've established that it's binomial. We've established that we could apply our normal CD or our normal distribution techniques. We've established what the mean and standard deviation are, but how do we actually solve the problem? Well, let's think about it. We know for our normal distribution techniques, there are two concepts, norm CDF and inverse norm. In one, norm CDF, we take our data value and we use it to find the area or the probability. In inverse norm, we take the area or probability given to us and we find the data value. We need to identify what's happening here. Well, the question they ask me is, what is the probability? Then they give me a data value. Given that the fact that they're asking for a probability and they're giving me a data value, that should trigger in your brain from 7.2 and 3 that we're going to use norm CDF. Well, what do I need for norm CDF? Well, see if you can pause the video and figure out how to fill this in. What's your lower bound, upper bound, mean, and standard deviation? Go ahead and give it a shot. All right. What's our lower bound? Well, if I go back up here, my lower bound, they want at least 8 of the water heaters to work. So my lower bound would be 8. What's my upper bound? Well, my upper bound, usually at this point, if I'm just doing greater than 8, is 1E99. And that would be appropriate to put in. Well, let's go ahead and go a step further. Interpret it in the context of the problem. Yeah, we'd say infinity typically, but we don't have infinite water heaters. We have 25. Okay? So at least 8 implies 8 all the way to all 25, lasting longer than 10 years. The mean is 6.25, which we calculated above. The standard deviation is 2.17. Now hold the phone before you type this in your calculator, because as you can probably see at the bottom of the screen, there's one more concept we have to cover. It's called continuity correction. I want you to look back at your book. You see, if you look at that middle chart, what you can see is they've actually have the histogram for the binomial probability we're calculating right now for our quick hot water heaters. If you look, you can see the middle of the graph is right at the mean at about 6.25, and then it works its way out. So why am I pausing you? Well, theoretically, according to our norm CDF setup, we're finding all the area beyond 8. But here's the problem. Binomial distributions produce bar graphs because they are discrete. This is a concept we talked about at very early in chapter 6. Normal distributions are continuous. You can see the binomial side of things in the jumps in the bar graphs, whereas that red curve, that's a normal curve estimating our binomial data, is continuous. Here's the problem. If you look very closely at 8, 8 lies in the middle of the bar. This is because our upper and lower boundaries are always plus or minus 0.5. We established this way back when we learned how to make histograms because we wanted our bars to touch. So the bar for 8 is really going from 7.5 to 8.5. The bar for 9 is going from 8.5 to 9.5, as you can see in your book. So what's the whole point here? Why am I stopping you from solving this? Because we can't plug in 8. If you look closely at the 8 bar, the 8 lies right in the middle of that bar. If I tell my norm CDF to go from 8 and beyond, I'm going to lose half of that 8 bar. Because the reality is that 8 bar goes from 7.5 to 8.5. What's the whole point? Well, because binomial distributions jump from one part to the other, we have to adapt our setup, aka continuity correction. We have to adapt our setup from discrete to a continuous. So what we need to do is for every lower bound, you must subtract 0.5. For every upper bound, you must add 0.05. This is called continuity correction. Whenever we apply normal distribution techniques to our binomial distribution, you must account for the continuity correction because the normal distribution is continuous. What it really boils down to, if you look back at the book, is I don't want to lose data. If you flip over to page 301, you'll see this illustrated again. The graph on 301 is trying to calculate the data from 6 to 10. But if we would do normal CDF from 6 to 10, we're going to lose half of the 6 bar and half of the 10 bar. What we need to do instead is subtract 0.5 and go from 5.5, and then add 0.5 and go from 5.5 to 10.5. This will ensure we cover the entire bar. So what does that mean for our problem? Well, it's going to be nearly identical setup, but it's going to be 7.5 to 25.5, 6.25, and 2.17. Again, account for your continuity correction. If you solve this in your calculator, what you will end up with is an answer of 0.2810. 0.2810. So what's the big picture here? Well, folks, we're applying normal distribution techniques to solve binomial problems because it's somewhat easier. Now, you might be sitting here going, that's not easier. I promise as you work with it, it gets a lot easier. Because norm CDF is easier to work with than binom CDF. You see, if we were to solve this as a binomial problem, which it is, they want to know at least 8 of the water heaters out of 10 years. Well, we learned way back in chapter 6, at least implies it's a range. So we would use binom CDF. At least is a form of greater than, so we have a 1 minus out front. Our number of trials was 25. Probability of success 0.25. They want at least 8, which means they want 8, 9, 10, and so on, which means they don't want 7, 6, 5, 4, 3, 2, 1. So we'll put a 7 in there so it sweeps away the 7, 6, 5, 4, 3, 2, 1, and the 1 minus leaves us with the 8, 9, 10, and so on, the probability of that occurring. If you would plug this in your calculator, you're going to get 0.2734. And when you look at our two answers, whether you solve it as a binomial problem or as a normal distribution problem, you almost get an identical answer. The difference is about 0.0075 of a difference. Minute. So here's the point, folks. We can take binomial distributions and apply the normal distribution techniques we've worked with in Chapter 7. We do this because norm CDF is nicer to work with than binom CDF. But here's the catch. We can't apply the normal distribution techniques all the time. We only get to do it if the original distribution is binomial and if n times p is greater than 5 and n times q is greater than 5. If it is and we want to apply the normal distribution techniques, we find the mean and standard deviation, and we plug it into whatever they're asking us for. If they ask us for a data, or if they give us a data value, and they ask for an area or probability, like they did here, we're going to use norm CDF. What we just have to remember is in that case, we got to account for continuity correction. That means we have to subtract 0.5 from our lower bound and add 0.5 for our upper bound. That way, as you saw in the picture, we don't lose any data. Folks, this has been 7.4. As always, let me know if you have questions. I will be happy to help you. Have a great day.